We don't really kind of use months, although there is a definition of Mars months, and they're kind of just defined numerically in 30 degrees of LS. So they're not, oh, someone has an open mic somewhere. So they're not uniform in length. Though kind of especially around here in the aphelion, the months are a lot longer than they are in this kind of short southern hemisphere summer. And kind of just again to kind of round off the timekeeping on Mars, one Mars year is about 687 Earth days, which is 668 Martian sols. And one Martian sol is 24 hours and 37 minutes. So it's very, very close to an Earth day. You'll also hear me kind of talking about Mars years. And these are given numerically. We talk about Mars year 1, 2, 3, 4, whatever. Currently in Mars year 34. And they were given in reference to April 11th, 1955, being the start of Mars year 1. Anything before that can be defined negatively. Anything after that defined positively. And I don't know why that date was chosen. It's just a common date that was chosen, and it's kind of become a method of defining Mars years. So seasons on Mars, as I said, they're not very symmetrical. You have this kind of short, sharp southern summer and kind of long southern winter. And one thing that's kind of, so these are taken at Gale. This is something just to note. In this lower panel here, you have the minimum and maximum average temperatures at Gale crater. And you can see there's a large variation between over a given point, kind of your maximum temperature. There's Celsius on this axis here and Fahrenheit on this axis here, depending on what you prefer. And this is Los Angeles, which for me is not very helpful. I've never lived in Los Angeles. So this is very, very roughly the Toronto maximum and minimum temperatures as a function of year. And so you can see that on like the warmest day in Gale crater, you can just about get to kind of the coolest days in Toronto. And on this side here, so this was your seasonal temperatures. On this side here, you've got your atmospheric pressure. And so kind of for reference, Earth is about 1,000 millibars. And Gale, it ranges from around 7 to 9.5 millibars. And you get this really interesting kind of double dipped profile. And this is due to the atmosphere kind of condensing and onto caps. And as I said, you had kind of a short season in one side and a long season on the other side. So in your long southern winter, you get this very, very deep cap. And in your short northern, long southern winter, you get this deep here. And then you get in the short northern winter, you get this kind of less deep dip. That's kind of something that's also really interesting. The average for the planet is around 6 millibars-ish. So this is just for Gale specifically. So kind of a little overview of the atmosphere. The atmosphere of Mars is mostly carbon dioxide. It's about 95% carbon dioxide. Then there are little contributions from nitrogen and argon. And then you get even more minor components, although some of these include ozone and can have quite an effect on the atmosphere. There is a very, very low surface pressure, as I mentioned before. Remember, Earth's atmosphere is about 1,000 millibars in comparison to the around 6, 7, 8, depending whereabouts you are and what time of year, millibars. And despite the atmosphere being very thin and very low surface pressure, we do actually see a lot of features that we are very used to seeing here on Earth. I'll kind of discuss those a little bit in each one. We see a lot of clouds at certain times of the year. We've seen fog, we've seen dust storms. And the interesting thing about dust storms is that you get kind of a lot of different scales. You get these kind of very small local storms. You see regional ones, which are much, much larger. And then we have these things called planet encircling storms or global dust storms. And you may have heard about it in the news recently, because there was one very, very recently, which I'll discuss later on in the talk. And those are actually visible from Earth and from orbit. From Earth, if you have a big enough telescope, but very, very definitely from orbit. And these images here on the left were taken by the Mars Global Surveyor in 2001. And this is kind of during a global dust storm, and this is during a kind of standard kind of dust-free time period. I believe that was actually taken only a month or two beforehand. And we also see dust devils, as you kind of used to seeing on Earth. And yes, in fact, they're only about 1 month apart. So this is an image, well, this is an animation of clouds that are viewed from Curiosity. As I said, depending on the time of year, we see clouds. So we have a cloudy season, which is in the aphelion cloud belt season. We've got, this is your LS range of about 40 to 150. Wait, if I jump back to here, I'm going to put in this region here, the Southern Hemisphere winter. And it should be noted, we also have, we have a cloudy season, we have a dusty season. The dusty season is kind of goes around your perihelion season. And something that should be noted is the clouds that we see from the surface are very, very, very thin. On the cloudiest of cloudy days, you'd be lucky to really catch anything. So to kind of bring out these clouds from the surface, we have to do a lot of image processing to pull out the differences between the frames. And these are actually some of the biggest clouds that we've seen from Curiosity. And they're very analogous to cirrus clouds here on Earth, which is pretty cool. And this animation here and this one here, they were both I believe it's 8 frames and last about 6 minutes in duration. This one's pointing directly upwards and this one's pointing towards the horizon, so you kind of get a sense of both the motion and the morphology of the clouds. So as mentioned, that we also have a dusty season, and these are two kind of trends of these are two data sets from 2 different rovers. So this is Opportunity on the bottom, and this is Spirit on the top here, offset. And they have been measuring the optical depth, so the amount of dust in the atmosphere. Curiosity does this as well, but these two are from Spirit and Opportunity. And what you can see kind of in general, this here is the global dust storm that I mentioned before, so kind of things go absolutely off the charts. But this is your kind of your general background. You've got kind of peak in your dusty season and your dip in your low dust season. As said, your dusty season is your southern spring and summer, which is that short, sharp, intense summer, and your low dust season is your southern autumn and winter. And you can see it's reasonably repeatable, excluding this kind of very sharp spike due to the global dust storm. And these are your Marsias along the bottom if you are interested. And so yeah, just something that I have been mentioning before, optically thick is when your tau is greater than or equal to 1, optically thin when it's lower than 1, and that's when you have kind of tau greater than or equal to 1, you've got a lot of absorbers or scatterers depending on what you're looking at. Oops, sorry. It attenuates your light substantially, and if you have an optically thin medium, you get much less attenuation. And so one thing to note is that your dusty season kind of in your southern hemisphere summer isn't mirrored by a northern hemisphere dusty season in the northern summer. Kind of everything dust related is kind of controlled by your southern hemisphere seasons. And so what we have here, is just to kind of illustrate that, is this is your latitude, your planetary latitude. Oh, I need to stop clicking. And along the bottom here is your time of year, your solar longitude. And this is your kind of spring, summer time in your southern hemisphere. And these are what we call zonal means. So you kind of take a band around the planet and you kind of have an average for that latitude range. So you're not kind of getting longitude variation in here, but we are seeing how things vary as a function of latitude. And you can see that kind of you have this very, very low dust region, and then you have this very high dust region. So this is the optical depth at 880 nanometers, which is very, very sensitive to the amount of dust. And this is an average over Marsia's 25 to 31, so it does include that global dust storm time period. And yeah, as I said, southern seasons control the dust. Why is that not moving on? There we go. And this is something that is very observable from the ground. You have, these are two images of this roughly the same direction. I'm sorry, they're not exactly the same, but you can see this peak here in on the crater rim. So this is the crater rim here, this peak, and this peak here are actually the same. And so this is kind of in a dustier season. You can see it's a lot less clear. You can't see many features. You can make out the crater rim, which is better than in at some points. And here it's very, very clear. And this point here to note is actually really, really far away, kind of 60, 80 kilometers away, whereas the crater rim in general is about 30 kilometers away on average. It does depend exactly which point in the crater rim you're looking at and whether you have any kind of foreground features going on. So these were taken with NavCam, the rover navigational cameras, and I'll kind of talk a little bit more about that in a moment. And the last thing I mentioned to you is that we see dust devils. And so these are taken again with Spirit, and you can find a lot more of them here. And Curiosity also sees dust devils. This is just my favorite kind of widely available one. You can see the number of dust devils going by. And yeah, so these are features that we see, very important for dust lifting, but they're believed to be, their activity during the big global dust storm is thought to be suppressed, which is kind of interesting. So Gale Crater, our science laboratory rover Curiosity landed in Gale Crater, and Gale Crater itself is just a little bit south of the equator, about 4.5 degrees south. And this is a topographical map, and this black line here, if you can see it, just about, we can't see it on the in the room here, but I swear it's there. This is where Gale Crater is sitting as of about 1900, and so that's its traverse. We've only explored a little tiny portion of it. And this blue region here is kind of your lowest level. This here in the center of this crater, just for scale, I should tell you, this is about 154 kilometers in diameter. And here's Aeolis Mons, which is colloquially known as Mount Sharp, and I'll probably just refer to it as Mount Sharp. It's a 5-kilometer high mountain in the middle. And this kind of mixture of this crater plus kind of mountain in the center has quite a strong effect on the atmospheric mixing, and which is visible through the amount of dust and the aerosol abundance within Gale. And so this kind of mixing suppresses something that's called the planetary boundary layer, which is the lowest portion of the atmosphere that is influenced by topography. It can be fairly turbulent on Earth. Outside Gale Crater, it's about 8 to 10 kilometers thick. Inside Gale Crater, it's only 1 to 2 kilometers. So that's something that is interesting, and it leads to decreased dust abundance here within Gale, and that is something that can be measured. We can actually compare the amount of dust inside Gale Crater to the dust outside of Gale Crater in the general atmosphere, which allows us to see kind of the difference, allows us to see whether they trend the same, and whether, for example, Gale is a source of dust, whether it kind of pushes dust out, or whether it's a sink, whether it just kind of receives dust from the atmosphere that kind of settles out. And so this is Curiosity. And she, as I mentioned, by observing the crater rim, the northern crater rim, which were those images I showed you before, you can determine how much dust sits between Curiosity and the crater rim. And this can complement images that she complements and measurements that she takes, specifically using images of the sun to measure the total column opacity, the amount of dust in the column of the atmosphere of the crater. So she's been observing the northern crater rim to do this kind of within Gale Crater optical depth measurements since Sol 100, and you can find that in Moore et al. 2016, another review, and also some in Moores et al. 2015. And that takes us up to Sol 1701. We're now on Sol 22 and something. And we've also been taking kind of similar observations with MassCam, which is a color which is an RGB imager. I'll show you whereabouts that is and kind of show you the difference between the images. Been sold 1200. And I'm not going to be talking much about the Mastcam, but something to note that they do exist, that we are kind of following up in color as well as in kind of this single red band that we get with the NavCam data. And yeah, so this and expands on Moore et al. 2016 and in review, and especially with regards to the 2018 global dust storm that I've mentioned a couple of times. So this is taken from Moore et al. 2016. You have your line of sight extinction measurements here in the blue triangles. This is your time of year. And here you have the column extinction values. And you can see, for this time period, you have, your dust-free season and then your kind of dust-heavy season. And so that has, as I said, it's now been extended up to Sol 1701, so it's a good couple of Mars years. And yeah, I'll be showing you an updated figure later on. So the cameras that I use are these ones here. These are the NavCam cameras. They have a 45-degree field of view. But for what we're doing, we use a 23 by 45-degree subframe, which is this here. And there have been several different observations, other observations done in the past, but this is the one we're currently using. And just kind of for completeness and the comparison, Mastcam, these two guys here, these have a 15 and a 5-degree field of view, and they allow us to do RGB imaging. And this is kind of comparing them all, taken on Sol 1933, which was a reasonably dust-free day. That one shouldn't be rotated, so I apologize for that, but you can see we get a lot of detail in the Mastcam images, especially the 5-degree field of view images, so we'll be able to get some really interesting stuff from these two. But this is what I'm focusing on currently. And one thing that I do prior to doing any analysis is I use information in the header files to correct for rotation, either due to the rover being not perfectly flat on Gale or any other rotation that you may get from imaging the Northern Crater Rim. So line of sight opacity, how do we actually go about calculating it? We use this relation here, which was derived in Moore et al., and it uses the radiance of the sky, the crater rim, and the ground to measure. You take ratios of the two, and you found that if you use this relation here, you can get the optical depth between the rover and the crater rim. So yeah, these regions highlight the regions that I've generally been using in this specific image. They're these ones. Sometimes the images are substantially more rotated, so you have to either increase the ground section so you actually get ground all the way along the image, but for the most part, they're kind of these regions here, which are described here, where 0 is around the base of the crater rim.
Could you talk a little more about where that optical depth calculation comes from? Do you have to assume a molecular opacity for the atmosphere?
Yes, so it's assumed that the material that forms the crater rim and the ground are formed of the same material. They kind of behave in the same way. It's also assumed that the ground region here is very low dust, kind of essentially has 0 dust between the rover and the crater, 0 dust between the rover and the ground section. And the ground section may actually be a couple of kilometers away, depending on the exact image you're looking at. And the crater rim, you assume the amount of dust that you're trying to look for, and the sky has a very, very high optical depth there. And this was actually tested and validated against a radiative transfer model here in Moore et al. And it was found that between the hours of 10 a.m. and 2 p.m. local true solar time, kind of taking noon as when the sun is directly overhead, it did give you correct answers to within 4%. So it has been tested and has been shown to kind of give good results within those timeframes. Outside of those timeframes, however, you have to kind of implement a radiative transfer model to get reliable results. And that's something because I'm working on as well, because we don't just take them within that time range of 10 a.m. to 2 p.m. We actually get quite a large variation in times, and we can get them very, very early in the morning, kind of 6, 7, 8 a.m. as well, and again, true solar time. And we can also get them reasonably late in the afternoon. And this, thank you for asking the question, because especially the having no dust between the rover and this ground section here is a very important assumption for later on, because in very, very, very dusty time periods, like we get during the most recent global dust storm, that actually completely breaks down, because you actually get a large amount of dust in this kind of ground dust-free section. And so we have to come up with alternative methods to do that.
Right, thanks.
No problem. And yeah, so that gives us the optical depth between the rover and the crater rim, but the rover isn't kind of stationary with respect to the crater rim. It does drive, albeit from Sol to Sol, there won't be a substantial variation, but say from Sol 100 to Sol 1700, there is, you know, enough of a difference to make quite an effect. So instead we use the extinction, so we can compare all these different sites, and we just divide by the distance. So the way we do that, because that also varies along the frame, because we have quite a wide field of view, again, this is 45 degrees, we use a digital terrain model, and this is a high resolution stereo camera. This is a digital terrain model from high resolution stereo camera data from orbit. And this digital terrain model is at 50-meter resolution. And so I use a method similar to Moore et al. In review, and it gives you a very, very accurate crater wall here to rover distance, both as a function of kind of grade, but also along the crater rim that you're looking at. The average is about 30-kilometer distance between kind of the rover and this crater rim, but it varies depending exactly on which point you're looking at. I'll show you a kind of a simulated view in a minute. And also, as I said, kind of as a function of kind of your distance along your image. And kind of to do that, we have to take into account both the telemetry that you can kind of see the traverse here, the pointing, because the pointing does vary a little, so exactly where your camera is pointed at, and the field of view. And for all of these images that I'm using of the northern crater rim, they are this 45 degree by 23 degree field of view, but I kind of later on kind of discuss some of the mosaics that can also be used to do this, and those have a very different field of view. And so kind of using this shows a wedge of kind of the visible region in azimuth, and then I kind of flatten that to create simulated views for NavCam. But as I said, this is 50-meter resolution digital terrain model, so, and that's 50 meters rather, linearly. So when you're creating an image from a wedge and you're kind of doing it in angular resolution, you do get an issue with the nearby regions having very, very few points. And as you can see here, this one's actually not too bad. But we do, in kind of later iterations of this, these are fairly early iterations, I interpolate along these and bin them. And that stops, for example, you getting, when we take images of Mount Sharp, for example, I was getting sections of the far side of the crater rim in my simulator, sorry, the far side of the mountain being visible just because of the resolution. So that's something that I kind of smooth out. So you get this very, very smooth image, kind of it looks a lot more like this kind of back region. This shows you the simulated field of view. This here, and there. You can see these features here. And as I said, it's about, on average, it's about 30 kilometers to the crater rim, but there are some regions that are, 35, 40 kilometers away, especially down here. There are some much nearer regions, 20, 25. So it can make quite the difference depending on which section of the crater rim you're looking at and what sol. And this is just an interesting kind of point of note. That we are actually able to see far, far, far beyond the crater rim on very clear days. And so this is somewhere in the kind of 50 to 80 kilometer region, depending on exactly which portion you're looking at. And this is confirmed with the mass cam. They actually saw that this kind of feature as well, where you see far, far, far beyond the crater rim. And yeah, as I said, kind of the near portions could be, you know, a couple of kilometers away. Usually a couple of kilometers is around this distance here. So kind of taking that and running them through, the relation that we discussed earlier. This top image here, this top panel here rather, is taken in that 10 a.m. to 10 a.m. to 2 p.m. time period. And these red points here are the results from Casey Moore's work in currently under review. And these are the updated ones using different regions, different methods. It's very good to see, at least in these ones, where there are kind of very similar. They do sit in the same region here and here. This kind of very kind of dense region of points is due to the global dust storm, and I'll discuss that in a minute. It's very saturated and then dense up, and I will discuss that in a minute. Here is the blue here is outside of that 10 a.m. to 2 p.m. time period. And as you can see, there's a lot of scatter, and that could be due to lighting effects. It could just be due to this method becoming less accurate outside that 10 a.m. to 2 p.m. time frame. So this is something that does require radiation transfer modeling, and that's something that is in progress, so kind of stay tuned. And I put this as a throwback to this is my initial kind of radiation transfer modeling from the TEPS summer school talk, so I meant to delete that, sorry about that. So this is the lighting effect. So you can see that there is a bit of scatter even when you have, even when you're looking at the kind of the time period where this model is very, very strong. But you do get kind of quite an effect depending on whereabouts on the crater rim you look. On those plots before, that was taking the whole of the crater rim and averaging it. So you average it first vertically, having done kind of having correct. Sorry, you get the optical depth as a function of crater rim position. And then you can correct for the distance to each point along the crater rim, and then you average it, and that gives you that kind of point on here. So if that's clear, so you kind of correct for both your distance and your relation to you do your ratios with the ground and ratios with the sky regions, and then average. But as you're kind of going along as a function of position, both kind of elevation and azimuth, you do see a lot of variation. And so this pink region here shows you the 1 sigma uncertainty in this vertical band here, and this is your optical depth on this side. So some of this could be real, some of this is likely real. There are portions of the crater rim and portions of the crater in general that are thought to be more dusty than others. Some of this is likely lighting effect, and some of this could be, it's lighting effect or your actual variation. So something that I'm looking at is kind of pull out that difference. I've been kind of looking at simulating the shadowing effects and looking as a function of time to see how these vary. We are lucky enough that we have some data, from example, from the same day, from very short time frames, where the shadowing changes, so we can look at how much that impacts it. But there can also be time of day variation as well, so you kind of have to be a little bit careful. And so yeah, so this kind of denser region here that I mentioned before is to do with the Mars Year 34 global dust storm. So I mentioned that you have kind of local and regional storms, and they're kind of the smaller scale, regional being the larger of the smaller scale. Once every few Mars years, these kind of grow into a planet encircling event, dust event, also known as a global dust storm. And this can lift dust really, really high up into the atmosphere, about 60 kilometers high. And it can take several months for it to kind of all settle out and settle down. And this can last a long, long time, as I said, weeks to months, and it gives us it affects the atmosphere very, very strongly. You get variation in atmospheric circulation. Temperature profiles and pressure profiles are affected. So the pressure throughout the day can vary, and that gets very suppressed. You can get dust devil activity, we believe, is affected, but the strongest ones that are visible from Earth is a change in the surface albedo. So how bright and dark regions, because you kind of get this dust lofted up, and it kind of smooths everything out as if you're looking from orbit or from Earth. And so this one here is the 2001 global dust storm, taken a month apart. And this was taken by the Mars Color Imager, MARSI, on board the Mars Reconnaissance Orbiter. And so again, it's a different camera, different instruments. That's why these two pairs of images look different. So these were May 28th, 2018, July 1st, 2018, and you can just see how different these two images look over the course of a very, very short time period. So this is the Mars U-34 global dust storm, also known as 2018. I will generally refer to it like this, the 2018 Mars U-34 global dust storm. And prior to the onset of this global dust storm, the Mars Science Laboratory Science and Operations team came up with a set of observations that could be implemented, a campaign that could be implemented if the conditions appeared to be right for the onset of a global dust storm. If we saw, for example, increases in atmospheric optical depth, and that are mirrored in other measurements that we take. And one of the things that this cadence of observation included was a daily image of the northern crater rim, so that we could monitor the dust between kind of Curiosity and the crater rim, and so then we could again compare it to the dust above. This was a big global dust storm, and the maximum optical depth was at about 10, and that was measured by Opportunity prior to it shutting down. We don't know whether that was its peak. The maximum optical depth recorded by MSL to date was 8.5, which is really, really high. Like, if you remember I didn't include it, so if we scoot back quickly to Spirit and Opportunities optical depth measurements, generally outside the global dust storms, 1, 1.5, sometimes 2, rocketing up to kind of 5, 6. This hit 10 at Opportunity and 8.5 at MSL, so which is very, very high. So we initiated the Global Dust Storm campaign on the 7th of June 2018, which was Sol 2075, and this continued for about 100 sols. And the line of sight image, kind of increased cadence of the line of sight images was continued for a week or two after that, so that we could monitor any kind of dust settling into the crater. Usually we take them about every 10 days. So now these were taken almost daily, and sometimes twice daily if we wanted to look at variation between the morning and the afternoon. And so this is kind of what we saw as the dust came in. And as you can see, there is a lot of dust. It's very, very, very thick. You can't see the crater rim at all by Sol, kind of 2083, 2084. And this wasn't actually the peak for the line of sight images. And this is day number here. And these are mostly taken in that time period, but not entirely. So there are a couple that are slightly outside of that, that 10 a.m. to 2 p.m. time range. But what you can also notice here is that this region here, kind of the ground region, you can see there is a substantial amount of dust. So the method that I was talking about previously does break down. And you can see it again here, kind of emphasized more clearly, like you can see that there is a lot of dust present in this ground region. The crater rim is entirely obscured. You get no even hint that you can see the crater rim there. So we found that this method breaks down, and we need another method. And so there are a few options. Visibility measurements is what I'm currently working on. I've also looked at contrast variation, so looking at trying to come up with kind of an automated way of finding the the maximum distance you could see looking at the variation along the frame and vertically up the frame. And then, of course, radiative transfer modeling, which will come into it later. But the visibility measurements are what I'm going to talk about right now. And so on Earth, they're used to monitor changes in how far you can see within in various atmospheric conditions, especially important in fog. You see fog visibility, how far you can see in fog. And so what I've been using is Koch-Mider's law, which relates to the daytime distance of the furthest discernible feature that you can see by eye. And so this is something I have been doing by eye, although that's also what I've been looking at, the contrast variation, to see whether I can pull that out. But I've been unsuccessful so far to your atmospheric extinction. So then we can compare that to the values that we've obtained before. This here is the contrast threshold, and this is the distance, the furthest distance you can see. Look, and happily, this is independent of time of day, so we can bring in these other measurements kind of outside of that 10 a.m. to 2 p.m. time. But I am also investigating on whether variations that we see, because we do see difference between kind of morning and afternoon, whether those are real or whether those are a lighting effect, kind of emphasizing features on the ground, for example. So using these line of sight images during the global dust storm, you have this very, very low, and then it jumps up and it peaks, excluding these high outliers, which could be due to actual diurnal, so time of day variation, or it could just be that difference in contrast that I was talking about. We get the peak at around Sol 2095, which should be noted is several sols later than the maximum optical depth that was measured kind of above the rover using sun images. And so that kind of suggests that Gale is behaving like a sink for dust, that dust is settling into Gale, which is really interesting and really good to know. We unfortunately didn't get anything in the kind of in the build-up days. It kind of went from, as you can see from here, kind of went to being not a lot to being a lot of dust very, very quickly. And even here you can just about see the crater rim at about Sol 2080. You can still see it, and then it kind of disappears around Sol 2082. And one thing that should be noted with this is, remember the scale. So this is going up to about 1.4. Previously, this was peaking at around 0.1. So this is a whole order of magnitude greater in extinction than we've previously seen, which matches pretty well with the amount of the optical depth kind of, from sun imaging, for kind of total atmosphere optical depth, which is also, as I said, it's around 8.5, whereas we usually see at maximum of 1 to 2. So these are, it was a lot of dust, basically. I'll get this for reference. And so that's kind of just looking in a pure north direction, the northern crater rim. But one thing that the rover does, and the rover was able to do throughout the global dust storm, Curiosity did not have to shut down. And it continued to drive, and when it drives, it takes these mosaics, and it takes these, part of that is taking kind of mosaics at the horizon. And these are, as you can see, they're a lot thinner than the images we've used previously that I was talking about. I don't have an image in hand. They are taken in 8 different azimuthal directions. And so this gives us other directions that we can look at and other ways of monitoring the dust, whether it's just as a function of time or whether the direction that we're looking has an effect. Although it should be noted that the direction, the distance you can see, even on the clearest of clear days, does vary as a function of azimuth. So, and also foreground objects. So this is all foreground. This here is Mount Sharp, this Aeolis Mons I talked about earlier. And this is Sol 2074. By Sol 2082, it was, almost disappearing, and has completely disappeared by Sol 2086. So as this can allow us to put limits on how far we can see in this direction, this east direction. Unfortunately, because of the foreground objects, we can't actually constrain it beyond whether or not we can see this far. But it, oh, sorry, I don't know what happened there. But it does allow us to at least constrain, if not kind of give complete, yeah, it allows us to constrain it as a function of direction as well as time, which is interesting. So kind of, yeah, as I mentioned, the north-facing one is the one that I've presented today, but this is something that I'm currently in process of working on. So kind of in summary, upgrade to the topography of Gale kind of strongly affects the atmospheric mixing, and we can use images taken of the northern crater rim to monitor how much dust is in Gale as a function of kind of season of year. We can find a very repeatable pattern year on year, and we can compare this to the dust above taken with sun imaging. And I've updated the line of sight record using those north-facing images through to Sol 2163. As I said, we're now on Sol 22 something, so I will be updating that further. But during the global dust storm, the dust was too thick. There was a lot of dust in the ground region, so an alternative method was required. North-facing results show us that the peak is more than kind of 10 times what had been previously recorded, and the peak is a few sols later than that seen in the column optical depth. And other directions are currently in progress, so I'll be looking at how they vary, whether the maximum seen is in line with the north-facing results, whether there's a positional dependence on the peak dust abundance. So kind of stay tuned for that. And then, yeah, I just wanted to mention the acknowledgements. So I'd like to acknowledge NASA, MSL Science and Operations Team, especially the Environmental Science Team Group, Canadian Space Agency, and so I'd be happy to take any questions if there are any.
Thanks, Christina. So I think there's a mechanism for me to check whether people have raised their hands. Yeah. So let's see what happens. If someone raises their hand with a question, in principle, I think I can see it. And maybe while people are figuring out how the heck to raise their hands,
how do you do that?
Yeah, you go to the participants, click on the participants button, and then at least I have a button that says raise hand. Oh, hey, well done. Okay, Ben, you're on.
Okay, thanks. So I'm sort of curious about these dust storms from a exoplanet's perspective. So this would be, not on a rover, and yeah, how is there some idea of the vertical extent? Obviously at the crater rim, when the optical depth is 8 or even above 1, I guess that means you're not looking through at any molecular sources, but like to the extent of the whole atmosphere, when these dust storms happen, would that mean like a spectrum that normally has various absorption bands and features would be flat?
So I have not worked on kind of spectra from the surface, but you do see that the albedo changes from orbit. So you can see these two here. Can you still see my screen?
Yes.
Yeah. So you can see that if you had sufficient resolution that you could kind of see the surface normally, that does get completely obscured during a global dust storm. So I would assume that it would have an effect, especially if you can detect dust using the spectra. Like I know it's possible to detect dust in other objects. I don't know from an exoplanetary perspective whether, I assume it's not there yet, but whether in the future potentially. if you could determine if there was dust in the atmosphere versus no dust in the atmosphere, I mean, that would definitely have a strong effect. We do also see changes in temperature profile, but whether it would be detectable from Earth from an exoplanet, I don't know. But yeah,
Sorry, just a kind of a follow-up on that question. How high up does the dust go, like in terms of atmospheric scale heights?
I was wondering something like
that. So it gets lofted up to about 60 kilometers in altitude. In terms of scale height, I would have to work that out, I'm afraid. I know absolute altitude-wise, it jumps up to about 60 kilometers.
Okay, are there other questions? Remember, you can just raise your hand. You could always just unmute yourself and start talking, but we may as well use the civilized technology we have while people are thinking of their own questions. So I want to make sure that I understand exactly what's going on in Gale Crater. So I guess I'll ask the following question: you said that there's less dust in Gale Crater, and I was trying to understand whether that was kind of like a bubble and there was plenty of dust overhead, but just not towards the crater rim, versus there's a kind of a cylinder of clear sky above the crater as well. And I think it's the bubble scenario. Can you confirm that?
Yeah, so I mean, Gale isn't dust free. There is a lot of dust that we see within Gale, as my kind of the images showed before. Just scoot back up here from where I had a mention of Gale specifically. So kind of the topography of Gale kind of does affect the mixing, kind of both from outside to kind of inside Gale Crater, and it's primarily this boundary layer suppression. I believe that kind of, it doesn't isolate Gale itself, but it kind of can reduce the mixing out to the outside. So kind of, yeah, it's not like there's this column of atmosphere that has no dust above it from kind of the ground all the way up. Does that help answer your question?
Yeah, I think that makes sense. And then my last question, because no one else has raised their hand. Oh, and by the way, Ben, I don't know how to do it, but there's probably a button for you to press to unraise your hand.
Oh, okay.
I mean, there must be some way. I don't know how, because I still see your hand. So my other question is, you mentioned that Gale Crater is a sink for dust. And so is that true in a year average sense, or only during a global dust storm? Like, is there actually more millimeters of dust accumulating? Like, basically, is the Gale Crater very slowly just filling up with dust?
That is what we are currently trying to figure out. So it's a case of whether Gale is behaving like a general sink compared to the outside, whether there are certain regions of Gale that are sources and some regions are sinks, or whether it's time of year based. So that is still something we're trying to figure out. And I believe Casey Moore's paper kind of looks a little in detail about the variation as a function of direction kind of within that general north-facing environment. So yeah, still in progress, still trying to figure it out.
Cool. Okay, I don't see any more raised hands. So at this point, we've got the co-Is, those of them who can stay on for another 5 minutes. I just wanted to quickly hash out some TEPS business, since they're online. So all the students and postdocs and stuff can sign off.